Hey guys, I've got a couple of cool reactions to share with you today. We are going to synthesize diiodoacetylene, a simple but quite interesting organic substance. First, we need to prepare a solution of sodium hypochlorite. To do this, I'll use the classic reaction between potassium permanganate and hydrochloric acid to generate chlorine gas. I'll bubble it directly through a sodium hydroxide solution, which will react with the chlorine to form the sodium hypochlorite we need in this beaker. Next, we need to generate acetylene. For this, I'll be using the classic reaction of calcium carbide with water. I'll add a few pieces of calcium carbide to a 2-necked flask. I'll fit a drop-in funnel with water into the top neck and insert a gas outlet tube into the right neck, directing the generated acetylene into another flask containing the potassium iodide solution. Next, I'll start cooling the flask containing the potassium iodide and begin adding water to the calcium carbide dropwise to generate the acetylene. As the gas begins to bubble through the potassium iodide solution, I'll start adding the previously prepared sodium hypochlorite solution dropwise. As soon as the two solutions mix, the mixture in the flask turns yellow due to the formation of excess elemental iodine. But in addition to iodine, the hypoiodide ion is also produced in this reaction. The hypoiodide ion can be considered a source of electrophilic iodine, which in alkaline conditions is able to iodinate alkynes. So, as we keep adding the sodium hypochlorite solution to the potassium iodide through which we are bubbling acetylene, the reaction mixture becomes increasingly basic. And over time, all the iodine will iodinate the acetylene. The solution's color will change from yellow to clear, and we'll see the flask fill with a white precipitate. The substance is diiodoacetylene. So next we need to separate this precipitate. To do this, I'm going to perform the separation using the classic method of vacuum filtration with a porous glass filter, which will allow us to collect the precipitate. This type of filtration is much faster and cleaner than using paper. Additionally, vacuum filtration allows the precipitate to dry much more quickly and thoroughly afterwards. And then I'll wash the precipitate in the filter several times with distilled water. After drying, we'll obtain this white powder. This is what dry diiodoacetylene actually looks like, but we can give this white powder a much more attractive appearance by using recrystallization. It can be easily dissolved in acetone. Then, after the solvent evaporates, we can obtain needle-like crystals of diiodoacetylene. To demonstrate this quickly and easily, I simply used a heat gun to direct a stream of hot air onto this acetone solution. The solvent evaporates rapidly, leaving behind diiodoacetylene in the form of fine needle-shaped crystals. The structure becomes especially clear when viewed in ultra-macro footage. If I dissolve diiodoacetylene in acetone and add a bit of zinc powder to the solution, iodine will be released. When heated, this compound decomposes quite spectacularly into iodine and carbon. Besides the purple iodine vapors and the soot, you can also see a flame forming. That made me curious whether it would decompose the same way in an inert atmosphere. So I carried out the next reaction in an argon atmosphere, and the decomposition was exactly the same. This proves that the decomposition of diiodoacetylene is not combustion involving oxygen, but rather an internal, fully self-sustained, exothermic decomposition. And this is how diiodoacetylene behaves when poured onto a heated surface. Diiodoacetylene is also shock sensitive and will explode on impact. Frozen acetylene is extremely flammable and will ignite on contact with chlorine vapors. Now let's take a look at the reaction between solid acetylene and liquid chlorine in slow motion. By the way, for my upcoming book, I've prepared a series of exclusive shots of this experiment. These are unique frames of these, and nearly 100 other reactions that are impossible to catch with the naked eye. Make sure to subscribe to the channel so you don't miss the announcement of the book's release, but the reaction of liquid chlorine with diiodoacetylene is not very impressive at all. So, as you might have guessed, I'm gonna show you the reaction between diiodoacetylene and chlorine vapors. To do this, I'll pour liquid chlorine into a flask and then lower the diiodoacetylene into it using a combustion spoon. In a chlorine atmosphere, diiodoacetylene rapidly decomposes, and along with a large amount of soot, hexachloroethane is formed as a byproduct. So now I want to show you the next interesting reaction. I've dissolved a small amount of diiodoacetylene in acetone, resulting in a clear solution that remains stable when exposed to air. Next I'm going to pass chlorine gas into this solution and see what happens. The solution remains clear and stable for now, while the gas is bubbling through, but once I stop the flow of chlorine, it quickly begins to turn yellow. However, as soon as I restart the flow of chlorine into the mixture, you can see that the solution quickly becomes perfectly clear again, but the moment I stop the flow, it turns yellow again. Share your thoughts in the comments on why this is happening. And of course, make sure to subscribe to stay tuned for more experiments, and if you'd like to support my channel, consider supporting me on Patreon. It's thanks to your support that I'm able to keep creating new chemistry content. Thanks for watching, see you in the next video.